The fourth question is on angular momentum and commutation operation. So let me get my pen. This over here, this L cap operator is the angular momentum operator. And if you notice, the definition is analogous to the definition for angular momentum in classical mechanics, where we have the angular momentum as a cross product of position and linear momentum. So similar definition over here is employed, completely analogous. Here, just these caps on top of these alphabets denotes the operator notation. So the question is, insert the definitions of the R and P operators, which is the position and linear momentum operators. Sorry, I should have written this cap over here because these are operators. Bar denotes a vector and cap denotes an operator. So insert the definitions of the R and P operators into equation 3.40 to prove equation 3.42. So here I have written down the equations. Equation 3.40 is the definition of the angular momentum operator, which is completely analogous to angular momentum of classical mechanics. And equation 3.42 is a commutation relation of the components of the angular momentum operator. So commutator of Lx operator and Ly operator is equal to IH cross Lz operator, and similar cyclic permutations. So when I say cyclic permutations, let me draw over here. So cyclic permutations means that if you go from x to y, x to y, y to z, and z to x, then it is with a positive sign. But if you go the opposite direction, so if you go from x to z, z to y, or y to x, that will give you a negative sign. And what this means is that the commutator of Lx comma Ly operator is IH cross Lz. Similarly, the commutator of Ly Lz will be IH cross Lx, and commutator Lz Lx will be IH cross Ly. And if you go the other way around, the commutator Lx Lz will be minus IH cross Ly. Commutator Lz Ly will be minus IH cross Lx, and commutator Ly Lx will be minus IH cross Lz. So this is what is meant by cyclic permutations. So x, y and z, they form a right-handed system, and this is how you go. So when you go clockwise, you get positive signs. If you go anti-clockwise, you just get a negative sign. And this is the form of the result that will be there. So now that we know the context of this question and we know what this question is about, it's about the commutator operation of the components of the angular momentum operator. Let us now look at how to solve this. So the position operator, if you recollect, it is let's say one component, x component is x cap operator, and this is just the number x, which is the position x. If you go into 3D, the 3D analog will be the r cap operator, which is the r position vector. And this position vector is simply x along the I, which is the x direction, plus y along the j, which is the y direction, plus z along the k, which is the y along j, which is y direction, and z along k, which is the z direction. This is position operator. Now momentum operator. If we look at the x component is minus IH cross del by del x, which is partial derivative with respect to x. And again, 3D analog of this would be minus IH cross del, which is the gradient operator. And this is simply, if I write it down in the component notation, del by del y along y and del by del z along z. Now if we look at the angular momentum operator, this is, or rather if you look at the angular momentum vector, because this is completely analogous to classical mechanics. So px component along the x, then py component along y, and pz component along z. Now if you recollect from basic mathematics and physics, this cross product is denoted as follows. It's the determinant of the following matrix. And determinant of this matrix is given as follows. We expand, let's say we are expanding along the first row, the top row. And now if we just change this to operator notation, so if you want to write now in the operator notation, so let's say now we look at the operators. So this is what it will be. This is for the equivalent for the operator notation. Now if we look at the components, these are the components. This is the Lx component, the component along the x direction, then Ly, and then the z component. Now we need to look at the commutator of these components. So first let me just briefly define what a commutator is. So commutator is an operation between two operators. Commutator, it is given by this operation. It is denoted by square brackets. So square brackets, and then you have these two operators, A and B operators, and this is basically the following: AB minus BA. So AB means first the operator B acts on the state and then operator A acts on the result, and BA means first operator A acts on the state psi and then the operator B acts on this result. And in general, it need not be the same, that is AB need not be the same as BA. So if it is the same, that if AB equals BA, then this commutator will be 0, and when we have such a case, we call them commuting operators. And when they are non-zero, when this term is non-zero, then these are non-commuting operators. And from the given result that we need to prove, you can clearly see that the components of the angular momentum operator are non-commuting. Now let us write down this commutator that we need to find. We need to find this, and by definition this is Lx Ly minus Ly Lx, and using these from here, Lx and Ly, we can plug in the expressions and then we will get the following. So let's put in for Lx then Ly minus Ly Lx. Now let us open up these brackets and let us multiply these terms. So you have y pz z px minus y pz x pz minus z py z px and then plus z py x pz. This is from this first term over here, these first two brackets, and then from the second two brackets we have the following: zpx y pz minus zpx zpy plus, sorry, not plus, negative, minus xpz ypz plus xpz zpy. Now let me just take the negative sign inside. I'm just taking the negative sign inside in this second bracket over here. Now let us group some terms together and see what we get. So if I group these two terms, let's say this with this term, let's see what we get. So if I'm looking at this grouping, we have negative y pz x pz plus x pz y pz, and this is actually, we can take x out because pz acting on x leaves it unchanged. It doesn't act on x, so x can come out. Similarly, y can come out because pz does not act on y, because pz has the term del by del z, and del by del z will not act on either x or on y. It will only act on z. So similarly, y comes out again. And this, if you notice, is the following commutator. It's the commutator of x operator with y times pz, or rather pz squared, which is 0. Why? Because this x y commutator is 0, and we can see this actually. Let us just take a quick look. So all these commutators that I'm writing over here, the commutator of the components of the position operator, these commutators are 0. And we can look at one particular example. Let's say the xy commutator. So that's basically x y minus y x, which is simply xy minus yx, which is just 0 because x and y are simply numbers. Similarly, you can see for the other terms as well, the yz and the zx commutator. Now let us look at let's look at some other pairings. Let's say this term with this term. So if I look at this particular pairing, let's see what this gives us. So again we have negative z py z px plus z px z py. Again, py does not operate on z, so z comes out, giving me negative z squared py px. And similarly, px does not operate on z, so z again comes out, z squared px py. And this you can easily now recognize from the definition of commutator. This is z squared times px py commutator. and this also is 0. And if I were to write down all these components, just like the components of the position operator, the commutator is 0. Similarly, the commutator of the components of the momentum operator, they are also 0. These are also 0. And we can look for one particular example. Let's say the xy commutator. So px is negative IH cross del by del x, and then py, and then the whole thing operates on a state psi, because an operator always operates on some state. So as follows. Then py px, so py is minus IH cross del by del y, and then px is minus IH cross del by del x, and the whole thing operates on a state psi. I squared is minus 1, so this gives minus h cross del squared psi over del x del y. Then here plus h cross squared del squared psi over del y del x, and the order of differentiation does not matter. So this is minus h cross squared del squared psi over del x del y minus del squared psi over del y del x, and because the order of differentiation does not matter, this is equal to 0. Similarly, you can look at the other terms. So all these yellow terms cancel out, the green terms also cancel out. Now we will look at the third pair. Let's say we look at this term over here paired with this term, the blue pair. So we have the blue pair. This is ypz zpx minus zpx ypz, and this equals the following. So px can as we saw, px pz commutator is 0. So whether we operate pz first on px or px first on pz, it's the same. So using that, I can bring px first and then pzz. And again, px operator does not operate on y, so we can bring that also out. Or so y can come front, so we have minus y px, and px operator does not operate on z, so we can take z inside like so. I need some space, so I'll shift this down a little bit. So we basically used this result over here, that px or on py or py on px, they are the same, and also px does not operate on y. So let me write down that result also. or let's say, let's first look at this. So this we can take ypx common, and once we do that, you see that this is nothing but the pz z commutator, and this is minus IH cross. So our final result is minus IH cross ypx. And how we got this? This is because of the following result. So you see, these operators do not commute. And also the position operator, let's say ith component times the jth momentum commutator, it is 0 when I is not equal to j. So this is delta ij IH cross. When I equals j, then you have this x px, and that commutator is IH cross. And when I is not equal to j, let's say you have x comma py commutator, that is going to be 0. And that is what we have used for this blue pairing. So x py commutator is 0, and that's why we could bring this y in front of this px over here in this term. And similarly, we could bring this px also in front from this result over here. And just to show you an example, let us look at this first x px commutator. So again we have x, then px commutator is minus IH cross del by del x, and this is, let's say, operating on some state psi. Then we have px operating on x and then the state psi. So we'll use the chain rule of differentiation in the second term over here. So del by del x of x psi is first term differentiation of first term times second term plus differentiation of second term times first term. So del by del x of x is just 1. So this gives us IH cross psi. And then first term times derivative of second term, and this term cancels out, giving us IH cross as the result. And similarly for this particular second commutator that I have written, one example, if we look at, let's say, x commutator py. So x py operating on a state psi minus y operating on x and the state psi. So this is equal to, let's just open up, minus IH cross x del psi over del y plus IH cross, and because del by del y does not act on x, x comes out. This gives the following, and this again is equal to 0. So this is how we get the pairing for blue. Now let us look at the last pairing. Let me just change the color of the pairing. Let's say red. So this is the last pair, and let us look at the expression for that as well. So the red pair, so the red term is zpyxpz, zpyxpz minus xpz zpy minus xpz zpy. This is equal to, let me just bring this down. I think I need some more space. Down to maybe here. Again, py does not act on x, or rather pyx and xpy are the same, we saw from the above result. So x can come out. This gives me xpy, and again py does not act on z, so zpy and pyz are the same, so z can go in, zpz minus so py commutes with z and py commutes with pz also. So py can come in front. So we have x py and then pz z. So I hope you understand this process, how we are doing. So if you look at the first term once again, so x commutes with py. So pyx and xpy are the same. That's how x comes in front of py. And also z commutes with py. So z, py and pyz is the same. So z can go behind py. So that's how we switched terms over here, and x and z also commute with each other. Similarly, in the second term, note that we can't bring z in front of pz because pz and z do not commute. We saw over here zpz, the commutator is ih cross. So pz and z order cannot be changed. But py commutes with z, so it can come in front, and then py commutes with pz, so it can also come in front of pz, and that's how py comes over here. So that's how we are making use of the commutator relations. So this is equal to, again xpy we can take common, and you can immediately now recognize this is nothing but the zpz commutator, which is equal to ih cross. Now we'll combine all these pairs, the yellow, green, blue and red pairs, to get the original commutator Lx Ly that we wanted. So therefore Lx Ly, this commutator, and the yellow and the green pairings added up to give 0. We were left with the blue and the red pairings. So writing down the blue and the red pairings, the blue pairing was minus ih cross ypx, and then the red pairing was ih cross xpy, and this, if you notice, is the lz term. So take ih cross common. This gives me x py minus y px, and this finally then gives me the desired result. Because we had written down the z component, if you remember, this is the z component, it is xpy minus ypx. So xpy minus ypx is lz operator. So this completes the result, and for the cyclic permutations, I will write down the result. So this is true for cyclic permutations as well. So if you have these components, if you are familiar with the tensor notation, you would know it can be written as follows. where this epsilon ijk is known as the Levi-Civita symbol. This right here is known as the Levi-Civita symbol. And let me write down for all of those who are not familiar with this symbol. So this basically means that the number, this epsilon ijk is a number, and this takes the value +1 if your ijk combination is equal to x, y, z or y, z, x or z, x, y. This epsilon ijk is -1 if the ijk term, this triplet, is z, y, x or x, z, y or y, x, z. And it is 0 if I equals j or j equals k or k equals I. So using this, you can actually write down the commutator for any pair of components of the angular momentum operator. And this is an important result. And this is the most general form of the result. Just like we have seen for Lx, Ly operators, you can repeat this entire process for Ly, Lz and Lz, Lz, Lx, and you will see that you will get this result in cyclic permutations. So this completes the question where we saw commutator of the components of the angular momentum operator.